Hi everyone. Today I'd like to talk about projectile motion. Our objectives here first are going to be to sketch the theoretical path of a projectile, to recognize the independence of the vertical and horizontal motion of a projectile, and finally to solve problems involving projectiles that are fired both horizontally and at an angle. So let's dive right in. First off, what is a projectile? Well, a projectile is an object that is acted upon only by gravity. So, for example, if I were to throw a baseball in the air, the main force acting on that baseball is gravity. But of course, we also know there's some air resistance. When we're talking about projectiles, however, we're going to neglect the effect of air resistance. So for the purposes of projectile motion, as we go through our calculations, there is no air resistance. It'll give us a model of what would happen without air resistance. Not completely accurate, but gives us a good feel for what's happening. Later on, once we get some calculus under our belts, we can go back and refine this model and throw in the effects of air resistance. Typically, projectiles are launched at an angle. They go up and down. Although, if you were talking practically, if you throw something up and down, that's a projectile. Typically, though, we're talking about things launched at angles. So, path of a projectile. A projectile launched at an angle will tend to move in a parabolic arc. And if it's launched from one height back to the same height, you'll have some symmetry of motion there. Just like we had with free fall, the time it takes to go up will be equal to the time it takes to go down. The total time in the air will be the time to go up and the time to go down, or twice the time up, or twice the time down. Also, if we launch an object up with an initial velocity of, say, 50 meters per second, when it comes back down to that same height, it will again be going 50 meters per second. Its velocity will be changed just the direction. The magnitude of the velocity will remain the same, however. The launch angle, if we launch it at 30 degrees, it'll come down at an angle of 30 degrees, just pointing in the other direction. So we can use symmetry to help us understand how projectiles function as well. So, the key to understanding projectile motion is this concept of the independence of horizontal and vertical motion. Projectiles launched at an angle, go up and down, really are just two types of very simple motion combined. There's the vertical motion, as the object moves vertically up and down. At the same time, it's moving horizontally. The vertical part of its motion is the same thing we were doing in free fall. The same math, the same equations all apply. Horizontal motion is even simpler. There's no acceleration on an object in free fall, in projectile motion, horizontally. It's not going to speed up or slow down. It will have the exact same velocity while it's in the air. This means that its acceleration is zero. The initial velocity is the same as the final velocity is the same as the average velocity. So that will simplify our problem solving considerably. And the key to making these problems work is keeping this horizontal and vertical motion piece separate. The only thing that you can transfer from vertical to horizontal motion is the amount of time an object is in the air. The amount of time an object's in the air vertically is the same amount of time an object's in the air horizontally. Finally, before we start our first practice problem, the other thing you have to keep in mind is an object is a projectile only while the only force acting on it is the force of gravity. So if I throw something up and then catch it, it's only a projectile when it is out of my hands. The moment I touch it, or the moment an object touches the ground, it's no longer a projectile. You have other forces at play. So only while the only force acting on an object is gravity can we actually use these projectile motion equations. So let's dive in and see how this works. Fred throws a baseball at 42 meters per second horizontally from a height of 2 meters. How far will the ball travel before it reaches the ground? Well, to start off this problem, let's kind of sketch what's going on here. If he launches the ball from 2 meters, it's probably going to follow a path something like that, a portion of a parabola. The height, it starts at 2 meters, its projectile motion path is going to end when it hits the ground, once it's traveled 2 meters vertically. Now, we know that it has an initial velocity in the x direction of 42 meters per second, and what we're looking for is its displacement, how far it travels before it reaches the ground. So we're looking for this delta x, its range, its horizontal displacement. Now, the way we start this is we're looking for how far it travels horizontally. So let's start by looking at the horizontal motion table. We'll call that our positive x direction and make our horizontal table with v naught, which we know is 42 meters per second horizontally. Our final velocity has to be the same because there's no acceleration in the x direction. There's nothing pulling it or pushing it sideways. We have our delta x, which is what we're trying to find. We have our acceleration, which we know is 0 because this is horizontal motion only, and time, which we don't know. So it looks like we know three things, v naught, v, and a. But in reality, since v naught and v, that's really the same piece of information. We could even say that v average is 42 meters per second. But that's the same piece of information. So we only really know two things, and we need three to use our kinematic equations. So we've got to find some way to figure out time. Well, how long the ball is in the air is really a function of its vertical motion. So let's backtrack and let's go look at this as a vertical motion problem first. Since the ball will travel down initially first, we'll call that our plus y direction, and we'll make our vertical table with v naught, v, delta y, a, and t. Since the object is thrown horizontally, its initial vertical velocity is 0. Its only velocity is in the horizontal direction, and since that's independent of vertical, the initial vertical velocity, v naught y, is 0. We don't know what its final velocity vertically is going to be, at least not yet. Delta y, we know it's going to travel 2 meters, and since it's going to go down, and that's the same direction we called positive y, that's a positive 2 meters. Acceleration will be 9.8 meters per second squared. Down is positive, acceleration is down, therefore that'll be positive 9.8 meters per second squared. And we want to find the time. Well, we can solve this pretty straightforward using our kinematic equation, delta y equals v naught t plus 1/2 a t squared. Thankfully, v naught is 0, that whole term goes away, so delta y is 1/2 a t squared. Or if I solve for t, t is going to be equal to 2 delta y over a square root. Substitute in with values 2 times 2 meters over 9.8 meters per second squared, square root, and I find t is plus or minus 0.639 seconds. And of course we'll take the positive root because that's the one that makes sense in this problem. Now remember, we said that you could not intermix horizontal and vertical motion except for one variable, time. The amount of time an object, a projectile, is in the air horizontally has to be the amount of time it's in the air vertically. So we can take this 0.639 seconds and plug it in over here on our horizontal table. Now we can use our kinematic equations to solve for the horizontal range. Well, let's use v average equals delta x over t, because we know v average, we know t, we're looking for delta x. If I rearrange that, delta x equals v average times t, or 42 meters per second, times our time, 0.639 seconds, gives us a total range of 26.8 meters. So a little bit more in-depth problem, but it's no more complex. We're doing the same math, the same physics, we're just breaking out horizontal and vertical motion. Let's take a look at another one. Here we have a diagram that represents the path of a stunt car that's driven off a cliff. And of course we're neglecting friction again. Compared to the horizontal component of the car's velocity at A, so we're looking at its velocity at A, what is the horizontal component of its velocity at B? This is kind of a trick question because if you remember, for a projectile, the horizontal velocity doesn't change. There's nothing accelerating it horizontally, so they have to be the same. Now you could look at this in a slightly different fashion and say, what about the vertical velocity? Well, of course, you have a smaller vertical velocity at A and a larger vertical velocity at B, which is going to keep increasing as the car falls. But it doesn't ask us about vertical velocity. It's only asking us about the horizontal component of the car's velocity. Therefore, the horizontal component of the car's velocity is the same the entire time it's a projectile, the entire time in the air. For objects that are launched at angles, however, we occasionally have to do another step first. We're usually given something like an initial velocity at an angle. Well, how do we deal with that? What we're going to do is we're going to break that up into components. A component that runs along the x-axis and a component that runs along the y-axis. Then we'll use those components as the initial velocities in our horizontal and vertical motion tables. Before we dive into a sample problem, one thing that's good to remember too, if you want any projectile to go the furthest possible distance horizontally, and it's launched from flat ground to flat ground, it comes back to the same height. The launch angle that gives you the maximum range is going to be an angle of 45 degrees. Want to hit a golf ball the furthest possible distance? You want it to come off of the club at 45 degrees. Hit a baseball the furthest possible distance? You want it to be hit at 45 degrees. Again, we're neglecting air resistance. That would add a little bit more depth and complexity to the problem. But in the absence of air resistance, 45 degrees gives you the furthest possible range. All right, let's take a look at our sample problem here. We've got Herman, the human cannonball. Can't imagine what life insurance costs for Herman. He's launched from level ground at an angle of 30 degrees above the horizontal with an initial velocity of 26 meters per second. How far does he travel horizontally before reuniting with the ground? Well, our first step here is to realize his initial velocity is a vector of 26 meters per second. And if I draw my axes here, that's at an angle of 30 degrees from the horizontal. Now, what I need to do is break this up into horizontal and vertical components that we can use. Well, the horizontal component, and if you don't remember these, go back to our scalar and vector lecture video, and it goes through this process, is going to be V naught x is going to be 26 meters per second, our total initial velocity, times the cosine of our angle, which is 30 degrees, should come out to be something right around 22.5 meters per second. We can do the same thing in the vertical direction as well. Vertically, V naught y is going to be 26 meters per second times the sine of 30 degrees, just taking the y component of that vector. Sine of 30 is 1/2, so I can fairly easily say that that's going to be 13 meters per second. V naught x and V naught y now I can go and use as my initial velocities when we go make our motion tables. Let's move to the next page so we have a little bit more room to work on this problem. Herman launched from level ground at an angle of 30 degrees with an initial velocity of 26 meters per second. How far does he travel horizontally? Well, this time, since we know a little bit more about projectile motion, let's use our heads and realize, we need to figure out how long Herman's going to be in the air. One of the first things we can do is realize he's going to go up and come down. Well, if we want to make life a little bit easier for ourselves, why don't we just look at the time it takes him to go up? If we do that and double it, that'll give us the total time Herman's in the air. We also know that V, y, right at that very top point is going to be 0. At the highest point, vertically, an object will instantaneously stop before it switches directions and comes back down, just like it did in free fall. Since we're only looking at the vertical motion in our vertical table, we can use that to our advantage. So let's call up our positive y direction and make our vertical motion table. We have V naught, V, delta y, A, and t. V naught, we figured out from our components on the previous page, was going to be 13 meters per second. Now, right here at the highest point, V vertically, we said is going to be 0. Delta Y, we don't really know, and it doesn't ask us how high Hermann goes, so in this case, we don't really care. Acceleration, we called up the positive y direction, so our acceleration is going to be down negative 9.8 meters per second squared vertically, and we're trying to find the time up. Well, that's a pretty straightforward kinematics problem. We know V naught, we know V, we know A, we're trying to find T. So we could say that V equals V naught plus AT, or T equals V minus V naught over A. Substitute in with values, with units, 0 minus 13 meters per second over negative 9.8 meters per second squared. And I get our time to go up as about 1.33 seconds. But we want the total time in the air. Well, if it takes 1.33 seconds to go up, it takes 1.33 seconds to go down. And with some rounding error, if I just plug that into my calculator, I find that my total time is actually 2.65 seconds. Excellent. We know how long Hermann's in the air. We just made our lives considerably easier. We're trying to find how far he travels horizontally. That means we're looking for delta x. So let's now make a horizontal motion table. We'll call to the right our positive x direction. And horizontally, we can make our table V naught, V, delta x, A, and T. And of course, remember, the one thing that can pass this artificial barrier between vertical and horizontal motion is the time. The total time Hermann is in the air horizontally is 2.65 seconds. We also determined his initial velocity on our previous slide using our vector components was going to be right about 22.5 meters per second. Horizontally, Hermann doesn't accelerate. He maintains the same velocity while he's in the air. So our final velocity horizontally is 22.5 meters per second, and our acceleration is 0. We're looking for delta x. And because V naught and V are the same, that's really one piece of information. We could even say that the average velocity in the x direction is 22.5 meters per second. So we could use our formula average velocity equals delta x over t, solve for delta x equals v average t, or delta x equals 22.5 meters per second times 2.65 seconds, substituting in with units, get a final answer, delta x, of about 59.6 meters. So once again, it looks more complicated because we're really solving two different motion tables in the same problem, but it's the exact same physics we've been using. Nothing really new here, just applying it in a little bit, in a slightly new way. And most of the challenge comes in bookkeeping, keeping our tables straight. A challenge for you. Can you take a stopwatch, a ruler, meter stick, or something to measure time, like your wristwatch, something to measure distance, and a ball, and do this lab at home? Roll the ball off a table or a desk. Then measure how long the ball is in the air using the stopwatch, and also how far the ball lands from the edge of the table horizontally on the ground. With that information, can you use what you know about physics and projectile motion to first off calculate the height of the table? Don't measure the height of the table, calculate it using that time. And secondly, can you find the horizontal velocity with which the ball left the table using both the time and the distance? See if you can do that and put it together into a one-page or less write-up that shows your data, your sample calculations, and a brief summary of what you learned doing this activity. Give it a shot, see what happens. And if you get stuck, check out aplusphysics.com. Thanks, and make it a great day.